A weekly spike is not an anomaly if it happens every week. Robust STL removes trend and seasonality. Then MAD exposes the residual points that truly break pattern. This gives you the pattern for a system that removes recurring behavior and flags unusual leftovers with a simple threshold. I'm Professor Pi, teaching AI foundations with simple Python. Seasonal anomalies are one of those things that quietly waste engineer time. You open a chart, see the same big peaks every week, and your simple alerting rules keep crying wolf. What we want is a rule that understands the rhythm first, then only rings on genuinely odd leftovers. Robust STL plus a MAD filter does exactly that. Model the cycle, then score the residuals so one big spike doesn't rewrite your baseline. This works well for daily logs and short-term telemetry where you want fast, explainable signals. Think of it as peeling an onion. STL peels off trend and seasonality, leaving a noisy core. MAD then measures how strange each core value is using medians, so a single spike won't drag the center or scale around. Together, they find the real surprises inside repeating data. We will build a tiny, clear pipeline that makes a weekly pattern, removes it, scores residuals with MAD, and produces ranked alerts. The goal is not fancy models. The goal is reliable, interpretable detection you can inspect and tune. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's build a tiny example that makes the problem visible. This snippet builds a small Pandas series where weekly peaks repeat on a predictable schedule. A raw cutoff sees every high weekend-like value as suspicious, even though those peaks are part of the normal rhythm. NumPy creates the day counter and repeating weekly pattern, while PD date range gives the series a real daily index. The line raw intentionally seb is intentionally simple, so the problem is visible. Thresholding the original signal mixes seasonality with unusual behavior. The output shows how many raw threshold hits appear before any decomposition, which sets up why seasonality needs to be removed first. Now we remove trend and seasonality so the spike can be judged in context. This example uses Statsmodels STL to separate the observed series into reusable pieces. The spike on 2026-01-20 is the kind of event a raw threshold should catch, but only after the recurring weekly shape has been accounted for. STL S period equals 7, robust equals true, tells Statsmodels to look for a 7-day seasonal cycle and reduce the influence of unusual points during fitting. The parts data frame keeps fit.trend, fit.seasonal, and fit.resit side by side, so the next step can focus only on residual behavior. The output shows that 3 components were produced, and where the largest residual landed. Next, we need a robust score that resists the spike itself when measuring spread. This code applies MAD scoring to the residuals left behind by Statsmodels STL. Instead of judging the original values, it judges how far each leftover error is from the typical leftover error. Resit.median gives a robust center, and the median absolute deviation gives a robust scale that is less sensitive to the spike itself. The threshold score, 0.3.5, is a common starting point for surfacing large residual deviations. Lowering it catches more borderline points, while raising it makes alerts stricter. The output shows the MAD filter narrowing attention to the remaining unusual residual date. We also want to see why robust fitting matters by comparing fits. This snippet compares 2 Statsmodels STL fits so the robust option has a concrete role on screen. With robust false, the spike can influence the fitted trend or seasonal component more than we want. The earlier fit used robust equals true, and robust resid checks how much of the injected spike remains in fit.resid after decomposition. Plain resid does the same for the non-robust fit. Then larger names which approach leaves the bigger spike-like residual. The output shows which fit preserved the anomaly more clearly for the downstream MAD detector. Finally, we wrap the pieces into a compact detection table you can iterate on. This example turns the decomposition and MAD score into a compact anomaly detection baseline. Expected adds fit, .trend, and fit.seasonal, which is the model's view of normal recurring behavior before residual noise. The result data frame keeps actual, expected, score, and anomaly together, so an engineer can inspect not just that a point fired, but what it was compared against. Sorting alerts by score puts the strongest remaining residual first, which is useful when there are many candidates. The output shows the final alert count and the highest priority alert date, completing the seasonality-aware detection loop. In a production mapping, you would run this daily on your web traffic or sensor logs, and write alerts to your incident store. The expected column helps explain why a point flagged, which cuts down on false positives from known cycles. What we did in 3 short ideas. First, we modeled trend and seasonality with STL, so recurring behavior doesn't trigger alerts. Second, we scored leftover errors with MAD, so one big event doesn't shift the baseline. And one caveat, pick the right seasonal period and tune the score threshold for your data. A clear next step is to tune the MAD threshold and the STL period against a labeled slice of your real dataset. For example, your daily web traffic for the last 90 days, and measure how precision changes as you move the score cutoff from 3.5 to lower or higher values. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.